Good evening, everyone. Welcome to this inaugural professorial lecture to be given by Professor Mike Duke. It's a particular pleasure to welcome Dr. John and Glenise Gallagher, who are here this evening, and they provided the generous endowment which created the Dr. John Gallagher Chair in Engineering that Professor Duke now occupies. Tonight, we're acknowledging Mike Duke's appointment to a professor in the School of Engineering. Mike completed his design apprenticeship, studied mechanical engineering at London's Southbank Polytechnic, graduating with a Bachelor of Engineering honours in 1987. For the next year, he was a graduate engineer at Smiths Industries in the UK, developing fibre optic temperature sensors for jet engines. For 17 years, from 1988, Mike was a research assistant, lecturer, and then senior lecturer at Southbank University. He was the course director of the International Mechatronics degree and the Bachelor of Mechanical Engineering. He was the founder and manager of the Southbank University Solar Racing Car Team and the Sustainable Transport Research Group. He completed his PhD at Southbank University in 1998. During 2001 and 2002, Mike was seconded to Solar Century Limited as their new product development manager and devised their product development strategy. He went on to become the co-founder and technical director of Solion Limited, a spin-out company that developed photovoltaic products, including the internationally patented, widely used sun mount system. Mike came to the University of Waikato in 2005, initially appointed as a senior lecturer, then becoming an associate professor in the School of Engineering. He went on to become the mechanical engineering program leader, founder and leader of the Agri-Engineering Research Group and Solar Engineering Research Group, and the leader of the electric vehicle research. He's actively involved in product development and innovation through research and teaching with a number of local companies. During his time at this university, Mike has received over $4 million in external research income, including a $2.6 million MB subcontract for robotics in horticulture. Currently, his main focus is leading agri-engineering research in the area of smart automation and robotics. The agri-engineering group comprises 4 academics, 5 PhD students, 3 masters, and 1 postdoctoral researcher. The group works closely with end users, engineering companies, and other research providers to develop solutions for the primary industries. Mike was appointed to the Dr. John Gallagher Chair in Engineering at the end of 2016. Ladies and gentlemen, will you please welcome Professor Mike Duke to give his inaugural professorial lecture entitled Robotics in Primary Industries, The Revolution Begins. Thank you.
Thank you, Vice-Chancellor. I think when you hear your CV being read out, you realise how old you are, which is always a bit of a worry. Today I'm going to talk about robotics in the primary industries. I believe we're at the beginning of a revolution in this sector, and I'm hoping that by the end of today's presentation or lecture, you will maybe believe the same thing. It's a controversial issue because some people say if we introduce robotics, we're going to take away people's jobs, but I'd like to hopefully make the case that isn't what's going to happen. Okay, so the first thing I'd just like to reiterate what the Vice-Chancellor said and really thank the Gallagher family for the support of the chair, Dr. John Gallagher Chair in Engineering. It's a big bonus for the School of Engineering because we are still relatively young, and we really do appreciate the support that we've got from the Gallagher family. So thank you very much for that. Okay, the first thing I'm going to do is set the scene because there's a bit of a story behind why we're even talking about robotics in the primary industry. And what we have here is a pie chart of New Zealand's merchandise exports for 2016. And if you look at it, it's broken into different sectors. And what's quite interesting, that if you draw a line, that little white line breaks it down into 2 parts. One is other and metals and so forth, and manufactured goods. The big chunk on the right-hand side, which comprises over 60% of New Zealand's exports is the primary sector. The primary sector being the dairy, the wood, the meat industry, all of those what we call the primary industries. So even though there's a push that we might move to a more manufacturing-based economy, we are still highly dependent on the primary industries, which is hence why I'm interested in how we can improve the primary industries using sort of robotics and smart automation. Coupled with that, the Ministry for Primary Industries have got a goal to double primary industry exports relative to 2012 by the year 2025. So this is a very demanding, very challenging goal to achieve. So that means we've actually got to double the exports since then in the primary sector. And it's a sector that is actually already running at quite what you might consider quite hot. So you're thinking, well, how are you going to make these different efficiency gains to get that, to double the exports by that time? And of course, coupled with that, this is where we come in as engineers. We've identified that the problems are being faced by the primary sector are things like this. This is from 2016. Fruit growers face huge labour shortage for bumper harvest. It's the old adage that it's really difficult to get labour in the primary sector, for example, harvesting. And a lot of the companies who we deal with will come to us saying, can you solve our problem? We cannot get the people to do the work. So that's one of the issues. So in one way, we've been told you've got to increase your exports, and then you've got these issues which stop you from doing it. The next one is change in labour legislation. So this is another news article saying that people who are using seasonal workers suddenly are facing problems with meeting the requirements of care for the workers. So it's a good idea to increase exports, but you've then got barriers being put in front of the producers that can hinder them getting that growth that's required. And so one is labour shortages. That's one of the biggest problems being faced. The second one we get is labour cost. Because of the labour shortage, a lot of New Zealand primary sector companies are actually importing labour from overseas. And we see this all the time. If I go off looking at kiwi fruit picking or seedling tree harvesting, I will not see many Kiwis there, or hardly any. It's all that work is being undertaken by imported labour, okay? And it costs a lot of money because there's a whole series, you're actually going through middle companies to provide you with that labour, and it becomes very expensive. The other one is labour legislation. So you've now got things about care, which is good for ethical reasons, but it adds another layer of complexity and cost to those primary sector providers. And it gets worse. You've then got quality control. For example, if you're harvesting forestry seedlings, then you have to do the quality control check when you're doing the harvesting. And suddenly you've got this imported labour who don't really understand quality control and really don't have any buy-in to the company. So you've now got a quality control issue with the harvesting, for example, harvesting. You've then got labour reliability. We've spoken to companies where one day they need 20 people to turn up to harvest all this, for example, seedlings, for example, and only 6 people turn up. So they then have to turn to the hired labour, bringing in imported labour, which then needs more training. So in fact, it's their biggest problem. They don't have a problem with the technology side of things. Really, it's a problem of actually growing the crop. It's a problem of the people that they're having. The workers are the biggest issue. And finally, not quite finally, but one of the other issues we add to that is health and safety legislation. So certainly the companies we've been dealing with are saying, look, we now want to come up with ways where we can mitigate or reduce the amount of health and safety injuries, because it's going up the line in the company through to the directors. So it's become another big problem. And the last thing that we've seen, and very interesting for us as engineers, is this one, which is obsolete machinery. So we'll go around to many different farm areas or primary sector places, and you'll just see old, antiquated machinery that doesn't match the needs of the modern era. It's really out of date, and it needs to be completely redeveloped. And of course, for us engineers, that's a good way forward. And so what I'm going to do with this talk, I'm actually going to use a series of case studies, which we'll move to in a minute, to show how we can sort of address some of these issues that we've identified. And so the question we're going to ask is, can robotics and what we call smart automation help solve some of the issues that I've just outlined? Okay? And at that point, everyone knows that I'm a bit of a history fan, So I'm going to move to a bit of, hopefully, if everything works well, a bit of history. This is a factory of 1930s, which is the Ford factory. And if you just look at that, you'll see that there are literally thousands of workers in that factory. And that's the way it used to be. You'd have tens of thousands of people clocking in every morning. They'd all be doing very repetitive jobs. Often they were dangerous, they were boring, there's a lot of dirt involved. And, I mean, if we're really honest, do we really think that is the way for the modern worker to be? And I'd say no. That's what we expect from a modern factory. All those jobs have been replaced with robots. And here you can see, if you're looking around here, you'll just see there's a few people wandering around, maybe a dozen or so. Whereas in the old days, there were thousands. And we've accepted that in a factory environment, robots are the norm. And even in China, there's a lot more robots being used in the Chinese industry. Do we really want to see people doing a mundane, boring job of, for example, sorting figs on a day in, day out, a mindless task? No, we don't want to see that. And in fact, if you go to a pack house in New Zealand, you won't see this. What you'll see is this, which is an automated system for sorting and grading apples. Now, this machine was actually developed in New Zealand by a company called Compaq. And what it actually does, this is a machine vision system. As the apples pass along these lines, they're rotated round and they go through that little camera there, and they take about 56 pictures of each apple, and they spread the skin out on a computer screen, and then a computer algorithm looks to see where the different quality of that apple is, and from that it can decide whether is this an A-grade apple or is it a juicer. The point, if you're a lucky A-grade apple, you become really expensive. So the challenge we've got is about, can robotics move from factories, where it's all very controlled, to the fields? Okay? So one of the issues we've got with this is, if you think about a factory, everything is controlled. You've got control over the space you have, and the same with the pack house. But if you look at this environment in the field, you can see that there are a lot of, it's not a controlled environment at all. You've got dappled sunlight coming through. You've got the kiwi fruit, in this case, in different positions. You've got leaves, you've got vines in the way. It could be raining. So, you are moving from a controlled environment to a much harsher environment that you have to work within. And this is one of the reasons why it's taken a while for robotics to move into the primary industries in the field. Good in the pack houses, good in the factories, but it's a big issue when you start moving it into the fields. And that's the challenge of our research group. So what I'm going to do is I'm going to start with a simple case study of what we call smart automation. And this work was undertaken in partnership with a company called Arborgen, who grow forestry seedlings. And they came to us with a problem of quality. They said, we cannot produce seedlings of the right quality. We've got a lot of rejections. And this work was undertaken by Ben McGuinness, and it was in partnership with Callahan Innovation. And it was all about dibbling. And for those of you who don't know what dibbling is, it's making holes in the ground so you can plant seedlings, for example. Here's a picture of, this is a forestry nursery in Tokoroa. Here you can see the worker there is got loads of little holes, and he's putting seedlings in these holes. What a pretty bad job. So the next one of the jobs we'll be looking at is how to replace that with an automated system. But you can see it's a very tedious job. And this is the dibber. So we talk about obsolete machinery. This thing is basically a wheel with spikes in it. And you might think, well, that's great, nice and simple. But as that spike goes round, it actually tears the dirt. So you end up with a V-shaped hole rather than a straight hole, which is what they need to do the planting. And so because of that, you end up with the seedlings all at funny little angles. They're all sort of ski-whiff. And when they grow, if you see here, you can see where the seedlings have all been put into the little holes. They're all at different angles. And then they can, as they grow with a sweep on them. And a sweep is rejected during the quality control process. So this is the type of thing that we're getting faced with by companies. And it leads to very nice little contracts. For example, a good Callahan Innovation contract with a good researcher like Ben McGuinness means that we can come up with solutions to that problem. And this is the solution. This is a replacement for the spoked wheel. Now, I've deliberately got Ben to make a nice computer graphic model of this, because the way that we actually design this type of machinery is done using what we call 3D CAD. So this is a virtual model of a dibbling machine. So this is an automatic machine. Instead of having spiked wheels, you've now got drill bits on it. It's got a little wheel at the front, which can, as it moves across, we can, with an encoder, we can pick up the position of it. And once we take that CAD model, we can convert it into a physical dibbler. And the engineers amongst you will be saying, well, how do you drill a hole when the actual tractor is being pulled behind it? And what Ben has done here, it's got a little computer on board, hence the smart automation, and it senses the speed of the tractor, so it knows the speed, and it's got a pneumatic ram that actually travels at the same speed of the tractor as it goes forward, as it goes down. So it does like a little V shape. And that dibbling machine has now been in operation for 4 years. And I think today we were estimating that it's drilled over 12 million holes for Arborgen. And it's a classic case of how smart automation can dramatically improve the quality in the primary sector. A relatively simple one, but I thought I'd leave this in just to give you a bit of an idea of where it comes from. And look at that. Perfectly straight seedlings, a beautiful flatbed. It took us ages to make this. And that's really what we're aiming for. And of course, the company were very happy. And it had lots of side effects. For example, with this one, we found that they could actually plant 2 at a time because they didn't have to sort of figure out what direction it went in. So they got productivity improvements, quality improvements, and if you look at the state of the bed, it didn't damage the bed as much either. So it was a very good solution. Ben McGuinness, who did this work, is a Waikato graduate. Such a good job did Ben do that Arborgen said, could you build a lifter grader machine for us? And we went, how hard can it be, we said. And so this, again, is with Arborgen and with Callaghan Innovation. And Ben was also being helped by 3 other Waikato students, Gordon and Jerry, I've forgotten the middle one there, Malcolm. Here we go, this is the problem. Lots of seedlings planted in lines, millions upon millions of them, 6 million roughly. And what you have to do, if you want to harvest that seedling, it's done by hand. You pull the seedling out the ground, you knock off the dirt, you take your hand up it like this, you then trim off the roots, and then you have to look at the root structure and decide, is that a good one or a bad one? And just remember now that there's very strict criteria for this. And so that's the problem. And so the way we do this is often we'll do what we call dirty prototypes. And this is something that any of the engineering students know that I'm very believe in. So we'll come up with a solution for this. So we're going to lift them using belts. We'll remove some dirt. And we then build a prototype, which is really crude and dirty, take it down and see if we can lift out the seedlings. And here we go. We're quite happy with this. We're not saying the belts was our idea, but ultimately we've used this idea and we've managed to pull the seedlings out of the bed and we can start to knock the dirt off it. And in effect, it's a part of applied research. It's also good for Arborgen because then they can decide, is it worth going ahead? Once they've decided, we'll produce a general arrangement drawing, and here's what we think the final machine will look like, which then goes to the client. So this is the lifter grader general arrangement drawing. Once we have that, we're now moving to the phase where we have to build something. But the next thing is we've got to actually turn it into a virtual 3D model. And this is it. It's a factory being pulled behind a tractor that will lift out the seedlings with the belts. It will knock off the dirt. It will trim the roots. And then it does the really clever bit, which is where you get your PhD work from. It drops them into a little box where it will grade them. And the grading is done using computer vision. So it's a computer vision control system. So up in this little box up top, after the roots have come off, it'll sit into a little holder. A camera will take images of the roots and the top and the side, and it will decide whether that's a good one or a bad one based on the criteria given by Arborgen. So there you can see the little device on the side. So it's got lights in it and cameras, and that all feeds into a computer, which then undertakes an algorithm to decide whether it's good or bad. Once we've done that, we have to manufacture the machine. And I'd like to make a plug here for our local company, Stainless Design, who are excellent. We can go from our virtual model of our virtual design of a lifter grader, and we can send the data files straight to stainless design based up to Tarapa. They'll cut them all out. They even weld stuff together for you. And basically, we can have a kit of parts for our lifter grade, which is really, that's a modern way to do it. And it's another reason why we can do this type of work in the primary industries. We also use a lot of 3D printing. That's become pretty commonly known. And right now, this is not, I wish it was full, I wish it was actually as fast as it goes, but it isn't. This is a time lapse. It takes about 8 hours to build something, typically with our 3D printers. And it's actually building this at the moment. And this is a part of a kiwi fruit harvesting robot. And you can see here that once it's basically actually built using additive technology rather than removed like the old way. This is the machine as it is as of a few days ago. So it's in the test phase down in the lab, and you can see all the belts and everything are working. And so we're probably 2 or 3 weeks away, maybe a month, from having all the wheels on and to go down and trial it at Arborgen. To me, this is a very, very ambitious project, and it is a tribute to Ben in particular, as a good old Waikato graduate who can design one of the most complicated sort of in-field systems that I know of. This is a smart bit. So what Ben's done here is use something called OpenCV, which is a computer vision software, and it's a library, and he's importing images of all the different tree seedlings. So they've come off, they've been harvested, and he's putting them through his little system. He's taking images of the root and the height and the stem, and from that, he's developed an algorithm based on the needs of Arborgen for grading, and he's basically got a tick or a cross depending on whether it's a good one or a bad one, okay? And so that took obviously quite a lot of time to do that, and it's a very smart piece of programming, and it's directly linked to the hardware. If it's good, it gets flipped off to the left. If it's bad, it gets flipped off to the right into a mulcher. So we did a study. So what we did, we took 200 seedlings, and we took the 3 best graders from Arborgen, and we compared the results of them grading the seedlings as compared to the algorithm developed by Ben. And what was amazing was that Ben's could grade as well as they could. So that's already been achieved. The other thing, so here's the final machine. Obviously, we're going to try and test this in a few weeks' time. We have to come up with a name, and we've called it the Beast because it's big and scary. Okay, so that's the machine, and hopefully within a few weeks' time, we'll see that operating. Another company comes. This is new research. I'm just going to give you an idea of what we're up to. Asparagus harvesting. So Tender Tips came to us, who grow asparagus, and said, we're having real issues harvesting asparagus, and so did Boyd's. And this was a really good opportunity to work with our partners, Robotics Plus, with a bit of funding from Callaghan Innovation, and all of these people involved in the work. So we've got Matthew Peebles and Mike Min as PhDs, supervised by myself, Dr. Lim and Al, plus 4 fourth-year mechanical students. The objective is to robotically harvest asparagus. And why do you want to do that? Because of this. If you had 100 hectares of asparagus farm, you have to walk that every day during the harvesting season, a distance of 600 kilometres. Now, you can't do that with one person, well, you could try, or you have to employ 80 workers, all of whom are imported. There are no Kiwis who do this work. It is back-breaking medieval work, and it's very expensive for the growers. So this is, the objective of this is to replace what is happening here with some sort of robotic system. And how do we do that? One of the biggest issues we have is actually trying to detect or find where the asparagus is. And so that's the current state of this work. So it's very new stuff. So here is a 3D printed bit of asparagus, and it's being moved. By the way, on the bottom left is a sensor called a LiDAR, which is a light detection ranging sensor. It's basically scanning a laser like this, and it's picking up the distances. And what it shows is that with the LiDAR, we can actually locate that kiwi fruit. And that's the work of Matthew and Mike at the moment. And with our new robot, thanks to CapEx, we can demonstrate the performance that we can actually detect this asparagus. So it's just early days for that piece of research work. Quite cool. And now what we're going to do is have a little look at what the LiDAR sensor is actually giving us. So if you look at it, on the right-hand side, those little dots you see are actually the robot body, and the little dots you see gradually, which occasionally move, are that asparagus. So it just gives you an idea of what the sensors are picking up. And because of that, you can actually get the XY coordinates of that piece of asparagus, which can then be fed back into the robotic software. And a new bit of software, a new system is being called Robot Operating System, which is being used by both Matthew and Mike for this work. And you can just see the way that you can control, see the position of the asparagus, and you can move the robot to that location, which now means you can start to detect this sort of asparagus in the real environment. Moving on, now this is the biggest research project we have, which is the Horticultural Robotics Project, funded by MB, the Ministry of Business, Innovation and Employment. It's a partnership between the University of Auckland, Waikato University, Plant and Food Research, and the industrial partner, Robotics Plus. So how much is this project worth? Well, it's with the input from Robotics Plus, it's over $10 million. So this is a very big robotics in the primary sector project. The objective is to harvest and pollinate, to harvest kiwi fruit and apples, pollinate apple and kiwi fruit flowers. What I would like the other thing on this one is, if we're going to do this work, we need to have something to put the robots on. And most of you are familiar with driverless cars. And what we can see here is the Google driverless car and how it's navigating around roads. Now, if we're going to have robots that are going to harvest kiwi fruit and apples, we're going to have something that can navigate around orchards. And so that's a key part of this research work, is to develop something that you can put on this pollination equipment or the harvesting equipment, and it can drive around. And here it is. This is called an AMMP, an Autonomous Multi-Purpose Mobile Platform, a very catchy name. And it's developed as a part of the research work that we're doing. And it's basically a large electric vehicle. So what we have on the back there are there's two electric motors at the back, two electric motors at the front. You can see it driving along here, so it all works. And so it's basically a four-wheel drive electric vehicle. All batteries are sitting under that area there, under the flat bit, with the controllers. It's got a little generator on there for generating electricity for running all the computers and for compressed air. So we've actually achieved one of the milestones of the MB contract, is to have an autonomous platform that can self-navigate around an orchard using LiDAR again. So it sort of scans the canopy of the orchard, and then it can self-drive around. And that's a collaboration between Auckland University and Waikato University in particular, with a lot of input from Robotics Plus, our major industrial partner. And I'll say it's a pretty cool machine. Okay, it weighs about 1.5 tons. That's one of my favorite things. Then got to harvest fruit. So how do we do that? Well, we know that if you just look at this, you can see one of the problems of the primary sector. You've got all these kiwi fruit at different angles, different heights. There's leaves in the way. There's, you get dappled light coming through, which can affect the sensors. And this is one of the early robots, which was used to move from place to place. This is an early prototype of the kiwi fruit harvesting arm. And this is the team. So what I'd like to point out is the one between the robot is Dr. Alistair Scarf, the CEO of the company, Robotics Plus. And here we got the team from Auckland, and this is the first prototype arm that is pictured here to harvest kiwi fruit. And we believe, we actually applied for a world record on this, but the Guinness Book of Records didn't get back to us on it. And this is the robot working. So what is happening at the moment is that there are cameras down below which are looking up at the canopy. They're using something called stereo vision. These digital images go into the computer software, and using OpenCV, which is computer vision, a 3D map of the canopy is created with the kiwi fruit. So you get the XYZ coordinate of each kiwi fruit. It then goes through a system of scheduling where it works out which way. It doesn't get them all. It's a prototype. Got to be fair. It's pretty tough stuff it's doing here. It's, sometimes it makes the odd mistake, but this was the first one of actually doing it. But we were pretty happy that we actually could harvest that many kiwi fruits successfully. And the other thing you might know, we talk about 3D printing, those gripper ends that you see, were actually all 3D printed in titanium. Because we wanted, you know why we did that? Because we could, right? Because we're engineers, and we went, oh, we could 3D print them in titanium. Let's do that. Was it expensive? Yes. Would we do it again? No. But it was fun. You know, we've all had you know what we've now printed? We're now printing in carbon fiber. We've actually got a 3D carbon fiber printer. So it's a very cool robot, and this was the first time it actually worked. But after that, you know, you have to go back and look at how to improve that fruit. You might notice that we think it's squishing too much on the kiwi fruit, which we've addressed with the new design. So there's the latest design of kiwi fruit harvester. And this was actually done by, we had a group of 3 mechanical engineering students. Here they are. There's Catherine and Parham and Kanan. And their job for the last year was to take the old kiwi fruit arm and turn it into a commercial one. And they did it. They did a fantastic job. They've basically got it to the point where it's commercial. And now there really is just a case of a few minor changes, very small changes, and then it's ready to be commercialized. And I'm very proud of what these students have achieved, that they come in at Waikato and they can go out and they can design and build machinery of that level. We should be very proud of what we've achieved. It makes me feel good as a lecturer knowing that we produce such high quality graduates. This is the current state of play. This was only taken a few days ago. So what we have here is we're going to actually have 4 kiwi fruit harvesting arms on this robot. But what we have here is just 3, and it's a test. We're now looking at, can we control where the arms are using the software? And this platform, you see the big black bit underneath, that's where all the computers are that run the robots. They are going to be bolted onto the platform, the autonomous mobile platform. The grippers will be put on, and then it will be ready to go and harvest kiwi fruit in a couple of weeks' time. So it's very close to having a full 4-arm robotic system working. Okay, and we're really excited to see if that will actually work out. So this is very much the testing phase, where we're just literally running each one of the motors and the actuators just to see if where we're saying it's going, does it actually go there? Okay. So after this, we've now got to, this is what the final beast is going to look like. It's another beast. It's going to have 4 arms on it, mounted on the autonomous platform, and that is then going to go around the orchard autonomously and harvest kiwi fruit. How crazy is that? A little side issue to that, we have to do apples as well. I don't know if you're aware, but apple orchards are being redesigned at the moment. Instead of having those lovely little round trees, they're being linearized. They're not being linearized because of robotics. They're being linearized because that you can get increased yield by pointing them towards the sun and linearizing them. It just so happens that it's also beneficial for harvesting because it's much easier to harvest on a linear system robotically than it is on round trees. So we had a group of 4th-year students, top quality students, who developed a prototype apple harvesting SCARA arm. And what it does, they did a lot of work with plant and food research on how to develop it. This is the prototype, beautifully laser cut and anodized with lots of 3D printed parts, the way we like to work. And the little arm at the end will go in, pick up the apple, suck it onto the little vacuum cup, twist it, and then drop it down into the slot. So that's 4 final year mechanical students who did this. And their project was one of the top 3 mechanical engineering projects in New Zealand. And here it is, little prototype. Sorry about the quality of the film, but this was done at the Engineering Design Show. And you can see here that Zara, who's one of the students, is just demonstrating the little cup goes onto the end with a suction. It does a rotation, that's all controlled by a computer. It then does a twist and drops it down the chute. What they did was they showed that it's possible to develop robotics for that application. One of the big ones is flower pollination. So this is a kiwi fruit orchard with all the flowers in them, and bees don't like kiwi fruit flowers, so it's pollinated in 2 different ways. One way is someone goes around and squirts each flower individually, and the other way is powder is thrown all over it. So one of the issues we had was to try and robotically pollinate them, and this is a game changer for us. This is something called deep neural networks. You've got to actually locate 200 flowers for every meter that you travel, and you're traveling at a meter per second. And so this method, which is like replicating the way the human brain works, was a training method, and it could actually recognize the flowers in real time, very quickly. It completely was a game changer, and it replaced a system that wasn't working properly, which was called stereo vision, which just wasn't quick enough. So, you know, words like game changer, I know they're used a lot, but it really is going to make a massive difference to the primary sector robotics by the fact that you can recognize these strange shapes very quickly, and then you can target them. So the only thing with this is we actually, literally that is on the cutting edge of technology. We had to buy in special computers that had the graphical power to do this, and they would basically, you can only buy them like one at a time. They were so brand new off the production line. You put it all together, and suddenly, you know, this is a part of Robotics Plus, you've got your autonomous mobile platform, you've now got your deep neural network machine vision system, and now we've got the pollination system on it. It's not a full pollinator, it's only got two booms, but this is a self-driving robot that is looking up at the canopy, recognizing flowers, and then hitting them with a spray of pollen. How mad is that? And it's actually happening. This isn't like something, this has actually happened just a few months ago. So this is brand new research results. And you know, there's still a lot of work to be done to really refine it to the point where it's commercial, but it's close to that commercial tipping point. The tipping point for these is you've got to travel over 1 meter per second and probably hit about 90% of the flowers. It's not there yet, but we're hoping that will be achieved about sort of November, December this year. So you have a look, you can see that the spray is going up and hitting the flowers. It's probably a bit too sprayy at the moment, a bit too vicious, and it's hitting the flowers, but the concept works. Okay. Other people have tried it, but this is probably the best example that we've seen. Interesting to note, if you've got a robot, it doesn't have to go to sleep. This thing can run night and day. You're illuminating the canopy anyway, and now you can literally spray them night and day, and therefore get the value back on that very expensive piece of equipment. And you're all probably going, blimey, how does this work? And the other thing, you notice how it misses a canopy? That's all done again using LiDAR, and it literally will scan the canopy and then move up and down relative to it. So here's a little spraying. So you just see it moving up and down, and that's just sort of keeping a distance from it. We've calculated that when it's at full speed, he'll have to fire 200 shots a second to hit the flowers. So it's pretty challenging. But yeah, it's very impressive. And this work, the pollination side of it's being done by Plant and Food. All the hardware is done by Waikato graduates. Okay, and then we work with Auckland University to link the deep learning. So we've got Mark Jones of Waikato linked with Auckland University researchers to get that working. This is a great opportunity for New Zealand to export high-value machinery and services. And that's one of the things that's been overlooked, is it's not just that we can produce, you know, we can improve primary sector efficiency and hopefully exports, but it's also an opportunity to export new products and services overseas. So you get 2 bangs for your buck. And so I think what I'd like to have hopefully said in a talk today, I know it's quite a short talk, 35 minutes, is that what we talk about as a vision for robotics in the primary industry, as something we're thinking in the future, well, I'd like to say to you now that A, it's needed, and B, that revolution has already started. It's on its way there. So anyway, I'd like to thank you very much for listening, and I hope you enjoyed a little review of robotic research at Waikato University. Thank you.
So, good evening, everybody. Kia ora, Kyoto. As the Dean of Engineering, it gives me enormous pleasure to actually give a vote of thanks for Professor Maitu's inaugural lecture. Certainly before this lecture, I never knew the word dibbling. I thought I knew a little bit about agriculture, but you know, that was a new one for me. But you probably sensed, many of you probably know Mike anyway, but the talk, I think, encapsulates his enthusiasm, energy, and dynamism, really, in this area of engineering, even to the extent of using titanium to make some gadgets or whatever you want to be doing. And actually, for us, that enthusiasm is really important because it's, from the short period of time I've known Mike, for 3 months, I can see it translates into both his teaching on the undergraduate program, research projects, and the major research programs you've just heard about. And actually, just reflecting on what you showed, Mike, I thought the black and white movie of car production in the 1930s as a comparison with fruit and veg picking in the 21st century was very telling. I hadn't seen that before, and I think that emphasizes the need to incorporate this sort of the automation and smart thinking. And in terms of exports, of course, it's a no-brainer really that you can see the same pressures on a much larger scale are going to be facing countries like the UK, who no doubt are wanting to strike some very good trade deals in the near future, I would have thought. So it's probably the last thing I should be saying really is that I could see that enthusiasm and dynamism that you into is going to be pretty critical really for the School of Engineering at Waikato. Because for those of you who know us, we're going through quite a period of growth, and I would say rediscovery. Rediscovery in the sense that it's emphasizing more about us being problem solvers, and problem solvers engaged in the outside world, which means in the short time I've been here, I've been very impressed in going around and seeing the work you've been carrying out, Mike, in the likes of Robotics and RAM 3D, where you see quite amazing research being carried out. And often those companies are very grateful for what you're doing because your research team are embedded in those industries, in their labs and their offices, and even the fieldwork. So that's a very impressive contribution to make in us defining ourselves and really differentiating who we are from the outside world. So if you could join me now really and give our thanks again to his presentation.